The learning component of the model includes crafting classroom activities according to the best principles of promoting learning. The principles of learning are active involvement, patterns and connections, informal learning, direct experience, reflection, compelling situation, frequent feedback, and enjoyable setting. More information on this can be found in the Technology as Facilitator of Quality Education model. The teacher leads the class in a review of the process of calibration so that the students can calibrate the pH probes they will use to test the pH of the water in the Green Hills stream. The teacher asks questions that activate the students' prior knowledge both of pH and the calibration process. The students describe the steps they must take to calibrate their instruments, and they highlight the importance of calibration for the accurate collection of data.
What else?
Like when it gives you a reading of volts or something, and you take a substance that you already know the pH of.
Okay, that's what I'm getting at. I get a substance that I know the
pH of.
Do I only use one?
No, you use two.
Why do I want to use two? Why isn't one enough?
To set a range.
To set a range. Excellent. Okay, so Robert, continue. I'm going to use the substance. Thank you.
And then it'll give you a reading of volts, and you have to set this many volts equals to the pH of this. Say you know the pH is 11 or something, and it gives you a reading of volts. You'd have to set it so this many volts equals to 11 for pH.
Okay, exactly. And that's just from one end. So maybe I've set my basic end, and what about the other?
As they describe the process of calibrating their pH probes, the students display active involvement in their own learning.
After everyone's done here and they're done, then you'll switch that, okay? Okay, now what are you going to remember to do as you are switching your probes? Excellent. Okay. Wonderful. Okay, now, they haven't done that yet, so why don't you hold on to this for a second, okay? And then we'll switch that.
As the students work in groups to calibrate their pH probes, they further display active involvement in learning. They are using liquids of a known pH to standardize their probes with the help of their Apple eMate computers. The teacher monitors the students, assisting them when necessary, but each group is responsible for calibrating its own probes. Instead of simply downloading default calibrations for their pH probes with their Apple eMates, the students have actually calibrated the probes themselves. This process helps the students understand the importance of calibration for collecting data.
Do you see how calibrating made this much more efficient a probe? What's that going to do to your data? What does that mean for your data when you go out there?
You could actually understand what it's saying, and it's going to be more accurate.
Oh, there you go. It's going to be more accurate. Okay?
The activity has helped students make patterns and connections between calibration and the accuracy and reliability of the data they collect. The students are analyzing their digital pictures of the Green Hills stream. They observe various features of the stream's environment, such as hills that may send rain runoff into the stream, a nearby parking lot that may account for some pollution, and trees that may cool the temperature in parts of the stream with their shade. After critical reflection on their observations, the students predict how different environmental features may affect the stream's water quality.
Would the soap raise conductivity? What do we know it might affect? What does soap affect?
The students are collecting data on the pH, temperature, conductivity, turbidity, and dissolved oxygen in the Green Hills stream. This activity gives the students an opportunity in which they can encounter science firsthand.
13.99.
Don't let the thing.
Don't let the.
Oh yeah, and Rashad, you might want to tip in.
I can't see though.
Don't fall over.
Okay, 609.65.
As they collect, record, and analyze their water quality data, the students gain direct experience with the process of scientific investigation. The students are comparing the pH and conductivity data that different groups collected at various sections of the stream. The teacher prompts the students to think about what the raw numbers actually mean for their water quality study.
Take a look at that. Okay? So think about that a little bit. We're starting off at about 1,500. What do we know about the water in the first section? Alice, what can you tell us about your section?
Really deep.
It's deep, and what else?
It has a lot of conductivity.
Right.
Bottom of a hill.
But if we look at it physically, you go out to your section, you say, that's a deep bunch of water. And what else do you notice about
It's
it?
slightly murky and really
Lightly murky. And what about movement?
Oh, none at all.
No movement. Okay? All right. Okay, so in section 1, I'm going to just kind of do this. And that's about section 2 a little bit. Okay, as we go through that. Let's go. It's still water, deep, and murky. Okay? All right, now, as you think about what's happening in your stream, compare it to this. You know, try and get this whole picture.
The teacher encourages the process of reflection when she asks the students to use their knowledge of the physical features of the stream to draw conclusions about how they could affect water quality. This also encourages the students to discern patterns and connections between different elements of their learning. She instructs the students to reflect on the relationship between the physical attributes of the stream, such as depth and water movement, and different measures of water quality. The students are constructing water quality models using the data they collected at the Green Hill Stream. With the help of Model Builder software developed at the University of Michigan, the students display their understanding of the relationship between seasonal change and different aspects of water quality.
All right, explain your model. First of all, from which way did you attack it?
We used conductivity.
All right.
That was our test, and we had the seasons, how long they were, affect everything in water quality. Because if the summer's longer, people are realize they're longer. But if the winter's longer, like there's going to be more road salt getting into the stream.
Okay.
Also, we have road quality, like the drainage systems by them. That would affect that. So if road quality was higher, even though it was a long winter, the water quality would still stay basically the same.
Stay basically the same. Okay.
When the students develop their models, they associate physical data collected at the stream with measurable factors. The students must recognize patterns and connections among the individual concepts they have studied, linking them together to form a coherent theory of water quality.